We will start continuous charge distribution.
Okay.
This is today's topic. It's on 1.35 page number.
Okay.
So till now I studied about electric field, electric force between two charges.
Yeah.
So generally what we did was we took a charge, isolated charge plus q, or we took some another charge minus q, right?
Yeah.
And this is a single isolated charge, right? So
Yeah.
if it is a positive one, we can say that it can be a proton, and if it's negative, we can say that it is an electron, right?
Yes.
So what happens in reality that these isolated charges do not seem to exist. We are There are few scenarios where we would find these charges as isolated, because see, what we have is we have atom, right? So inside the atom we have nucleus, and then electrons are revolving in different orbits. This is nucleus, and as a whole, like, it is quite difficult for an electron to be found outside the atom, okay? Because
Yeah.
they become unstable when they are outside. Everything wants to keep itself stable. To keep themselves stable, electrons are held inside the atom. So you won't find these isolated charges in reality, right? So what happens is we generally observe immense amount of charge at some point, at some space, right? Like we can have this box
Okay.
just for drawing purposes, or we can have some sphere which is having some charge q, right? This is
Yeah.
not a single charge. This is not 1.6 into 10 to the power minus 90. That is a small q, okay? Minus q or plus q. Plus is for proton and minus is for electron. This capital Q means whole charge is situated. And you can find another case like this where you have some charge. So charges are found in nature in bulk, right? That is called as continuous charge distribution. And when charge is spread in a region, it is called continuous charge distribution, right? Charge is spread in some region. For example, you can have a thin strip and its breadth can be assumed as nil. It has only length, so it can have a charge q, okay?
Yeah.
There are three different charge types of charge distributions.
Okay.
One can be volumetric charge distribution, in which there is some volume in which a charge is there, right? So for example, this
Okay.
cuboid. Second is what? Surface charge distribution, in which there is surface area. For example, there is a rectangle or a square on which there is some charge. It does not have a
Okay.
height. Its height is assumed as nil, right? So
Okay.
that is called surface charge, and other is linear charge. In this case, you have
Okay.
a strip which does not have any width or height, right? It only has a length,
Yeah.
and the
It's just
charge
not
is
on a
there,
line.
distributed charge all over its length.
Okay. Yeah.
So there is this and continue. So suppose uh, we are given a charge distribution, right?
Yeah.
And we need to find the force due to the charge distribution. So let's say I draw some charge distribution. This is not a single charge, other charge distribution. This box, right?
So there's multiple charges.
Like you cannot isolate a charge, it is continuous. For example, there is a seed of wheat, and not wheat, let's say some grain, mustard,
Okay.
or you say even salt, right? If there is a grain of salt and when there is a heap of salt, so that is continuous. You call it as whole self a whole thing, right?
Yeah.
There is self a whole thing. It is composing of small bits of salts, right? So if this whole salt is called S, then we may call each bit of salt as DS, very small salt.
Okay.
But we cannot isolate each one of them, right? We cannot isolate each DS from this. It is assumed to be a single piece of charge, which is S.
Okay.
So there's no way we can isolate, right? Same
Yeah.
here, we assume this as a continuous bulk of charge or piece of charge, right?
Yeah.
And let's say at a point away from this, at a distance r, right?
Yeah.
We need to find the force on a charge q naught placed at this point, correct?
Yeah.
Same thing as we did for two charges. Earlier we had two charges and we need to find the force, let's say at B, A and B. This is Q1, Q2. So you can find the force at B due to A. Similarly, here we want to find the force at charge Q naught due to this bulk charge, okay?
Okay.
And each small bit of this charge here is, let's say, called, should we call it, let's say it is dq, all right?
Okay.
Right,
Yeah.
like we did here for salt. So it's nothing to process. How can we do this? We know that the force is given by force between two charges is given by k q1 q2 r square and r vector unit vector. This will be the force vector. Here what we will need to do is, since we have bulk of this charge, right, and we have assumed this small piece of charge as dq, so what we can do is, um, let's suppose take the smallest bit of charge in this bulk, right, which is dq. Okay,
Yeah.
and let us find the force due to that bit only, not the full one.
Yeah.
Are you getting it? So we need, this is composed of
So,
dq1 plus dq2
so,
plus dash 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 dqn, isn't it? There are many millions of n here, so we need to find the force due to each, because since I told you this in another class that if there are many charges placed, q1 q2 q3 q4, and we need to find the force on the charge q placed at this point, so you need to find the force due to each one of these charges on q, right?
yeah.
You cannot leave anyone because each one of them is having an impact on q. Similar is case here. What you are doing is you are having small dq charges, n charges, and you need to find the force due to each dq, right?
Yeah.
So what we do is we find the force due to each dq, which is called as df, very small force, because each dq is small, it will exert a small force df, isn't it?
Yeah.
And that is the same formula, k q1 q2. So k, what is q1? dq. What is q2? q naught divided by r unit vector, isn't it? This is the charge, this is the force on this q naught due to each single piece of dq charge.
Yeah, but when that takes so.
Yeah, so there is a method to do that which is called as integration.
Okay.
All right, that's a
Yeah.
good question. So we will not add them manually. There is a mathematical analysis that takes care of that, and we have formulas already that we can use to find this whole force whole force f. So we will not add df1 plus df2 plus df3. This is taken care by integration. Now how we'll do that, let's see. Let's erase that. Is this well, right? Now we have found force due to 1 dq. We need to find the total force, isn't it?
Yeah.
So the total force, which is given by F, right, is equal to, it is actually, if you say in layman terms, it should be df1 plus df2 plus dash 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 dfn. But in actual terms, what it is that we can sum, because since they all of them are identical dqs, right?
Yeah.
They are identical dqs, so what we do is we take the force due to 1 dq and integrate them using this symbol. This is called as integration.
Uh,
Integration means actually to add up, right? Isn't it? The usual meaning is to add up. Integrate means to make thing combine, right? So this will be called as f. And how to calculate this? So this would be calculated by formulas, with the help of formulas, right? Which we will study in maths. All right.
Okay.
Yeah. But what you can do here is, you can do one thing. You can at least uh, replace this df by this formula, isn't it? So f would be equal to integration of, this is like a snake, so k dq q naught upon r square
That's for our
r
cap.
cap, right? And what we do is, uh, in integration we only take the variables in here, right? So we take out the constant term, for example k and q naught.
Can you give me a second? Just 1 minute. 1 minute.
Yeah,
I'll be right back. 1 minute.
okay. All right, so this is how we do this. Now you can take the constant out. So in integration, while finding integration, you take the constant out. So k q naught upon r square integration of dq r unit vector.
Okay.
Now we have to solve it generally. We solve this also. We used to find this integration.
Okay.
I'll tell you later how we find this.
Okay.
So this is the continuous charge distribution. Now let us discuss each one of them. So first one is volumetric charge distribution.
Okay.
Volumetric charge. So in, let's say we have this volume.
Yeah.
Volume you can see in the book as well. So what is the each small piece of its volume is named as dv, and each small charge is named as dq, corresponding to the volume,
Yeah.
isn't it? Because each small charge will take a very small volume, which is called dv, and the whole volume is called as v, capital V, right?
So,
Is capital V. Now again take a point at a distance r, okay,
yeah.
which is, let's say we want to find the force on q naught, right, at a distance r away from it. So in this case, whenever we have these charge distributions, we take uh, what we use is, we use the density of whatever distribution we are given. Here we are given density of volume, right?
Yeah.
So we use this concept because the density is everywhere same. Let's say you are given a volume of a tank. This is a water filled in. This is, let's say, a cylinder, right?
Yeah.
So if you find its density, let's say it's water in there, so 1000.
If you
Okay.
would?
If there is some liquid in there, right?
Yeah.
And its density is 1000. Okay.
Okay.
So at every point you can say that it's the same, you know?
The density, yeah.
Yeah, density is the same.
Yeah.
So that's why we will use this thing here also. We want to find the force at this point. So let us find the first the density of this volume. So and we call this by the name rho,
Rho.
HO.
Okay.
This is a symbol used to denote a volumetric density. And what is density?
Mass upon volume.
Here it is mass, okay, but here we want to find the charge density. There is no mass
Okay.
here because the charge is being distributed, right?
Yeah.
Whatever is distributed, we want to find the density of that. So it will be charge on what? Volume.
Yeah.
Charge per unit volume will be the density, isn't it?
Yeah.
And if the volume is a sphere, correct,
Yeah.
of radius r, capital R, then we can replace this volume by 4 by 3 pi capital R cube, isn't it?
Yeah.
In that case, this q is the whole charge on this volume, right? And dq
Yeah.
is the small charge. Now I said since density is same at every point, so for the small dq also the density will be the same. For example, if you want to find the density at for a small charge dq, then it would be dq by dv, that is small volume taken by that charge.
Yeah.
Okay, and now if you cross multiply this, so what you will get is dq is equal to rho times dv. That you should, let's say it is equation first.
Sure.
Now let us go back to the thing that we need to find. We need to find the force on this charge q naught due to the entire volume v, right?
Yeah.
So what would that be? First of all, can we find this small f? Can we find?
Small what?
Small force will be df due to this dq,
Yeah.
and that would be what?
And that would
K
be
q
2.
dq by r square r unit vector.
Yeah.
And if you want to find the whole force F, what we need to do is we need to integrate this thing, right?
Yes.
So integration of df, which would be equal to integration of k q naught dq by r square r unit vector, right?
Yeah.
You can verify it as well. And in the book here it is
Yeah.
written as suffix v. Can you see? Below the integral symbol it is written as v here. Okay, that v means, that is a symbol,
Yeah.
okay, that v means integration over the volume. There are different type of integration over the surface. This is the volume, right? So here we
Yeah.
will integrate over the whole volume. That means we will add all the components in this volume, which are dq.
Okay.
If it had been s, which we'll study in a moment, it means surface integration.
Okay.
So in that case we add all dq's on the surface, and if it is L, it means linear on the along the length only. So in that case we would add all the elements of dq along the length, because in this case there is no width or height of that strip, right? So this volume integral over the volume v k q naught, and you can replace this dq as rho times dv, right? Rho times dv.
Your voice is breaking.
What?
Your voice is breaking.
Oh, let me see it. uh, Internet is all right. Are you getting a voice break now?
Not no, but when you were saying that
No, we just replace this dq with rho times dv. Tell me if there is a voice break again, I'll check it.
No, I think it's from my side.
On your side?
Yeah, because I got a notification and it said that I'm having some internet
So it must be your internet issue, right?
Yeah.
Everything is okay at my side. This is the force. F is this thing. A dq rho times dv r square on r unit vector. Now in this you can take out the common things which we not need to integrate. So q naught is the constant,
Yeah.
k is a constant,
R squared.
yeah, rho is a constant, and everything else inside the integral. So now we have found v. We can also find electric field, because electric field is what? Force divided by that charge.
Yeah.
Okay, so force divided by q naught. That's it. Okay. So this is due to the volumetric charge distribution, the force at q naught, right?
No.
In the similar way, we can find the force due to surface charge. Everything else is same except that we have a surface here. So in this case, we will draw a sheet like this. It does not have a height, right? It is devoid of any height.
Okay.
It has a length and a width on. That's why it's called a surface. Okay. And in this case, let us assume another point at a distance r. Right?
Yeah.
And another, in this case we assume this as s, and this is small surface as ds, small charge as dq. Okay.
Yeah.
But charge density in this case is not rho. It is given by another symbol, sigma. Sigma.
Okay, sigma.
It's just the notation used to denote the surface charge density, right? So surface charge density would be what? Charge per unit surface, per unit area?
No.
Charge per unit area. What is the area of a sphere if we take it as a sphere, the surface? 4 pi r square, isn't it?
Yes.
4 pi
R squared.
r square. And it can also be written as, due to the small charge dq, so dq by ds, isn't it?
Yes. Yeah.
And if you cross multiply, dq is sigma times ds. Everything else we are doing the same analysis.
No.
So now we will find df, which is what?
Which is integral. Oh,
No,
wait,
small force.
Sorry.
K,
Sorry, small force. K, Q. I mean,
q,
K, D,
q naught,
1, Q naught, R squared, R cap.
right?
Yeah.
And the whole force F will be the integral of df, which will be the integral of this thing.
Yeah.
And you can replace this dq by sigma times ds. So k dq is sigma times ds, q naught by r square. Everything else is same, all right? We can now solve this and find f. Just everything is same. But integral you cannot solve, I have not told you, right? This is due to the surface. I forgot one thing. So what will be the SI unit of this volume charge density? Charge per unit volume, that is coulomb per meter cube.
Okay.
And for this sigma, what will be the SI unit of sigma?
Same thing.
Coulomb per meter square.
Uh,
It is on the surface. The area
Alright.
area will be there. Now last is the linear charge distribution. Can you do it on your own? And everything else is same. We'll do it quickly, right?
Yeah.
So in this case, we will have length, charge on a length, right?
Yeah.
Which is devoid of any width or height. So like this, we can have single line of charge, right?
Yeah.
And this density is called lambda.
Lambda. Okay.
Okay, so lambda is the linear charge density, which will be charge per unit length. Okay,
Yeah.
so the length of a wire, suppose this is a wire, right? And if we make it into a circle, okay,
Yeah.
same wire is made into a circle, right, by bending it. So
Yeah.
its length will be equal to the circumference of this circle.
Yes.
So because since this charge density is lambda, which is charge per unit length, so in place of length we can write the circumference 2 pi r,
Yeah.
because the length of this wire is the same as the circumference of this, isn't
Yeah.
it? Furthermore, this lambda can be written as dq by what?
What are you asking? Oh, sorry. DQ upon.
dl,
So
right?
DQ lambda.
dl.
Yeah.
Now you can find df, a q. I'm not assumed. Let's say there is a q naught at a distance r naught from it. So k q naught dq divided by pi square r. And here we will assume this small length dl, right?
Yeah.
And the small length dl has a charge dq.
Yeah.
Okay, just a second. So we can find.
Fire alarm.
No, it is a normal alarm of my mobile phone, because I am unable to wake up with normal. It is very loud.
I know. I got scared.
F is equal to the integral of df. That's it.
Okay.
And the lambda SI unit of lambda is, or should be less than less unit of lambda, charge per unit length.
Per meter.
That's about the charge distribution. Okay. And now let us do a question on this. Can I erase this? Everything?
No, I didn't write it.
Okay. Now I should continue.
I only write it.
You can write, I'll share you later. You can, or you want to write on now? Okay, you can write. So
Okay, so I wrote. Wait, I don't.
okay, so the first question is, let me copy. Mm, for some reason I cannot read.
Okay, which question is it?
It's example 45. Oh,
Yeah, well,
there is a surface. Okay,
yeah, surface
I'm
density.
briefing it for you. There is a surface, and the charge density is sigma.
Two.
It is given as 0.7 coulomb per meter square, right?
Could,
What?
sorry,
Okay.
nothing.
When its charge is increased by 0.44 coulombs, so when charge on it is increased by 0.44 coulombs, what happens
Yeah.
is the surface charge density is increased by 0.14. Sigma increases, is it 0.4? 14?
Yeah,
14, is it correct?
kilometer square. Yeah.
What he's asking? We need to find the radius of the sphere and initial charge on it. So find radius, this surface sphere, and initial charge on the sphere. What do you mean by initial charge? He's asking when the sphere was having a surface density this much, what was the charge on the sphere at that point? That is called the initial charge on it. I should tell you this. What is this? That there is a surface whose surface charge density is 0.7. Correct?
Yeah.
That means sigma is what? Charge per meter square.
Yeah.
Charge per unit area. There is this area of radius r, right? And it should have a charge. That's why it's having a surface charge density. Now what happens? It is given, this surface is given an additional charge. It is distributed all over it. It is 0.44 coulomb. When you give it an additional charge, no, 0.44 coulomb, then obviously its density is gonna increase because the surface is the same, the radius is the same, and you have given an extra charge to the sphere. That means charge per unit area will increase.
Yeah.
So that increase is given by 0.14. So the net density would be 0.7 plus the increase, isn't it?
Yeah.
That is the sigma in the second case. We need to find the radius of this sphere and the charge on it. How we can do? Any guess?
With this, what do you call this? Line charge distribution.
There is line, there is surface charge distribution.
Oh, sorry. Oh, no, because it says find out the radius.
Radius?
Nothing.
Because sigma is given, so there is surface.
Yeah. Right.
Cannot be a line charge when this sigma is given. So you can just invoke this formula, simple, the density formula. What is this formula for density? Sigma is charge on 4 pi r square.
Oh, yeah.
Apply this in both the cases. In the first case, what we have? Sigma is given to us, which is 0.7 is equal to q is not given. Is q given? No. Upon 4 pi r square. R square is also not given, I think, right?
Yeah.
So this is the first case. In the second case, what happens? The density is 0.7 plus 0.14.
Yeah.
And the charge is how much now? Charge is increased. No. Charge is 0.44 is additional given to us. Charge will be q plus 0.44, isn't it?
Yeah, upon 4 pi r square.
The second equation. Now what can we do using both of these equations? Can we find anything using these? What we can do is we can divide 1 divided by 2. Okay,
Yeah.
so when you divide 1 by 2, so 0 0.7 divided by 0 0.7 0.14 is equal to k upon 4 pi r square, not k, q, and q plus 0 0.44 upon 4 pi r square. So this cancels out, right?
Yeah. Yeah.
And what you get, 0 0.7 divided by, tell me how much it will be.
0.1.
0 0.7 plus 0 0.14.
Is it not 0.2?
This,
Yeah.
how much it would be?
0.7 plus 0.14 is 0. I think that was wrong.
84 q
0.84.
upon q upon
Got it.
this. Now this, you can see we have eliminated r using both of these equations by dividing them, and we only have q in this equation. Now you can cross multiply and find the q.
Q.
Okay, find this.
Okay.
Let me write this. Be 2.2. Okay, q would be, yeah,
Okay.
hello, it would be 2.2 coulombs.
Okay.
What is this q?
The charge.
This is the initial charge, all right, when the density was
Yeah.
0.7. So we have got the initial
Yeah.
charge. We have not got the radius, so what you can do is you can substitute
Charge.
q in equation 1 or 2, let's say 1,
In
and
one.
find r. Okay, so
So we get,
0.7 is equal to 2.2 upon 4 pi r square,
yeah.
and so
Cross.
yeah, you can cross multiply 0.7 into 4 r square is equal to,
Yeah.
which will give
So
r square,
is equals to 2.
and r, if you remove square you get under root.
No.
So this will be the r. If you solve it you will get 0.5 meters. Okay, this is the answer.
Yeah.
All right.
No.
Okay, this is the that we did. Okay, so now let us do a question on the electric field due to dipole that we studied yesterday, right?
No.
Do you remember the formula for electric field due to a dipole?
Oh, I guess.
Is E axial?
Wait. I think it was. Okay. I think it was 2.
What two? E axial.
Was it not 2?
Is it?
Like 2. Like 2. P upon r
2k
square
p
with
by
p
r
vector.
cube, I think.
Or was that q?
There is no q is not there.
No. I said 2k
P
upon
divided by r
r.
cube.
Yeah.
That is the electric field at the axial point, and it is given in the direction. If you put a vector here,
Yeah.
it is in the direction of dipole moment, that is from negative to positive charge, right? What is E equatorial? Minus
Minus
kp
k
by
p
r
vector
cube
vector.
in the negative direction of this P, right? This is the formula for electric field. Now let us do a question.
Okay.
Okay, let us start with a small one. This is example 50. There are two charges, plus 5 microcoulombs and minus 5 microcoulombs, and they are placed how much apart?
I'm going to the question. Okay, got it. They're placed 1 millimeters apart.
1 millimeters. Find the dipole moment. What is P? The formula?
P is q.
Q into 2a. Q is how much? Either of the two, 5 into 10 to the power minus 6.
Yeah.
And what is the value of 2a? This whole is the value of
So,
2a, remember.
yeah.
So it will be 10 to the power minus 3 meters, because we need to
Yes.
find it in SI.
Yeah.
So 5 into 10 to the power minus 9. Okay,
Yeah.
and it is coulomb meter.
That's right, P.
This is the answer. Now let us do another one. Let us do question number 53. Okay, so these formula that I wrote here, these are approximate formula, right? These are not the exact formulas, remember. Yeah, can you hear me?
Voice is really bad.
Why it is bad? I don't know, because I can hear you properly, and I think
Your
there
voice
is.
is like stretching and then it's breaking, distorted.
But these are approximate. The exact formulas are the ones that I told you before, assuming A is less than X, isn't it?
Yeah.
You don't need to remember them. But the question is of only this kind. So let us do some other, I think. Do
Example 56.
Yeah, I am seeing that only. It's again the formula on the whole actual formula.
Okay.
Can do 55. Okay. 55 would be good, I think. 5 is, let me try to copy it. This is number 55. Two charges are placed at 5 millimeter apart, plus minus 10 coulomb. That means they consist of dipole, isn't it? Five millimeter distance. Minus 10 micro plus 10 micro. Then determine the electric field first at a point P on the axis of the dipole 15 centimeter away from the center O on the side of the positive charge. So on the side of the charge is this. Let's say this is the point P, which is 15 centimeter away from the center to the center. That means he's given us R, right? R is 0.15 meters. Can I write?
Yeah.
And 5 millimeter is the 2A value. So 2A is how much? 5 millimeter, which is 5 into 10 to the power minus 3 meters.
Yeah.
And Q, either charge is 10 into 10 to the power minus 6 coulomb in magnitude, right?
Yeah.
Now let us apply the formula. So for the first part, we are given a P point on the axis of the dipole. So let's apply the formula. What is E axial? 2kp divided by RQ in the direction of P. So 2kp, 2k, what is P? Q into 2a. Q into
Q is 10.
2a is 5 into 10 to the power minus 3. What is R? R is 0.15. So 0.15 Q. And what is K? I have not substituted. It is 9 into 10 to the power 9. Isn't it?
Yeah.
So this minus 6 and minus 3 would be minus 9.
Yes.
And this can be eliminated with this plus 9, isn't it? So what you get is 2 into 5 into 10 is this 0.15 cube. That's it. T divided by, no, that's not 5 to the 10, 100. 0.15 cube. What is the answer? It is 2.66 into 10 to the power 5. And that is Newton per coulomb. Okay?
Yeah.
Electric field is Newton per coulomb, right?
Yes.
Force per unit charge. So this is the electric field axial, and direction will be in p cap direction. And the second part is what? We need to find at a point Q 15 centimeter away from O, passing through O and normal to the axis. That means at some point, that's it, this Q 15 centimeter away from the center.
Yeah.
You can also write 0.15 meters. So in this case, what we will do, we will find E axial, not E equatorial. It is minus 2kp by r cube in p unit vector. So minus 2 into 10 to the 9 into 10 to the power 9.
9.
Q into 2a. Q is 10 into 10 to the power minus 6. 2a is this time around same thing.
Yeah.
So plus 2a.
Um,
5 into 10 to the power minus 3. This is minus 3 power divided by r cube. R is 0.15 cube. 9 and 9 cells. 5 to the 10, 10 tens a 100, 900 minus 900, 1.1 cube. And what you'll get solving this?
okay.
1.33 into 10 to the power 5. Unit vector, right?
Yeah.
This is Newton per Coulomb. So this is the answer. Okay.
Yeah.
These are some questions on this.
Okay.